I think your audio may be off, or I don't know if it's muted.
Yes, thank you. Can you hear me now?
Yeah.
Okay, would you like me to repeat the lesson? Because I did the whole thing. I'm kidding. I tell you, what plays real well in the classroom does not play on the internet. Okay, so can you see my piece of clay? Okay, so imagine this piece of clay is one atom, and we're going to bond it to two other atoms. So imagine there's an atom here where my hand is, and we're going to use this little stick to show that bond. And we won't leave my hand there because it just gets in the way. So we want to look at the chemical bond. That's this stick here. Then we're going to put another atom on the other side, like where my other hand is. And this stick will represent the chemical bond. All right, so you've got your central atom, the green clay, and the two atoms outside. Now, the valence shell electron pair theory, which we talked about last time, says that, well, electron shells repel each other. So how could we arrange these two bonds so that the electron shells will get as far apart as they can and be equidistant? Well, what if I did this? All right, I don't know if you can see that. What if you did this? Is this equidistant and far apart as possible?
No.
No. Tell me where to move it, Nicole, to make it better.
Directly opposite from each other?
Yeah, directly opposite. So if you have the clay and sticks or something like that at home, build this. This one's pretty simple, but build it anyway because it lays the foundation. So how many people can actually build this at home? Just Nicole, you the one who has the sticks?
Yeah.
Okay. All right. Matthew? I saw your hand go up. You have a question?
I was to say, I do have clay and stuff. I just have to find it wherever it is. But I know I have some somewhere.
Okay. All right. So I'll wait for Nicole. Nicole, did you build this yet?
Yeah, sorry. I'm just dealing with my dog being annoying.
Your dog is what kind of dog do you have?
It's my friend's dog because she's having family problems, so I'm kind of watching him now.
Oh.
Hold on, let me see.
You're a good friend. That's cool. All right, so here we have our first bond, and there's a name for this. This is called linear. You have three things in a row, and that's the best arrangement. It's linear. Oh, good. I could see. Thank you, Nicole. Thanks for sharing. All right. Now, let's take an example of another element that's like tin chloride. How do I do this? I don't know. Can you see my paper? I can't see it all. Can you see my paper?
Mm-hmm.
All right. So you see this beryllium fluoride here? BeF2?
Yes.
No? Yes? No? All right. So if you were to draw the Lewis dot formula for this, I don't know. Can you see this clearly?
Yes, but it's upside down.
It's upside down. What if I do this? Is that better?
Yep.
Okay. So I'm holding the camera with one hand and drawing with the other. So this is as awkward as it gets lately. So You have beryllium, which has 2 electrons, and fluorine has 7. It needs 1 more. So if you were to draw the Lewis dot structure for that, it would look something like this. Notice that there is no extra electrons on the beryllium. All right, it's an exception to the octet rule. Right, 4 electrons. It's just cool with 4 electrons. That's an example of the model that we drew. That would be a linear molecule. Raise your hand if you get that. Okay. All right. If you didn't get it, then think about asking me a good question. All right. So here we have tin chloride. All right. So tin has how many electrons? What family is tin in? Okay, so so if tin combines with chlorine, I think tin has 4 electrons in its outer shell. So it could share 1 electron with chlorine, another electron with chlorine. So then chlorine will still have its octet here, including the 2 that are being shared. So now you have a bond. Let's draw this over here. So we have tin with a bond to chlorine and a bond to chlorine. All right. Now you might think this would be linear, but it's not. Let's not forget about these electrons over here. There's a lone pair of electrons. All right. That's an electron domain too. So if you were looking at the electron domains for this, right, the electron domains would be trigonal planar. You'd have 1, 2, 3 things in space. All right, now bear with me while I switch camera here. Oh boy. Okay, I'll be right back. I gotta run and get a balloon. I'm blowing up the balloon. I know you can't see it because my camera's like hidden. So all right, I'm back. So here's our molecule again. This time it's tin is represented by the clay, and you've got 2 bonds to each of the chlorines. So you might think it'd be linear, but look what happens if you put these. This balloon represents the 2 electron, the lone pair of electrons. What's this going to do to the electron clouds around these 2 atoms here and here? It's going to stay linear or what?
Bend.
It's going to bend, right? This extreme electron density here is going to push these 2 bonds down like this. So now you can see where it's trigonal planar. You've got 3 things in space, right, spread out, and they're all in one plane. So I tilt it this way, you can kind of see they're all in the same plane. All right. Now, trigonal planar would be the name of the electron domains. So there's 2 things here. They get very confusing. If we're asking you for the shape of the molecule, that's a different question than asking you for the shape of the electron domains. when you look at the electron domains, you consider all the electrons in bonds. Like this is a bond, so you consider that one. This is a bond, you consider this one. This is lone pair, you also consider that. So you got to consider all that. You do not consider the extra electrons that are on the chlorines and the peripheral chlorines here and here. Ignore those. All right. So if I were to ask you, so typically I would give you the formula SnCl2 or the name tin chloride. Then you'd have to write the formula, and then from that you'd have to predict the shape. And the traditional way to do that is to do the Lewis structure, and then look at all the electron domains. The electron domains here are trigonal planar, but to name the shape of the molecule, you ignore this here. You just pretend it doesn't exist. So this molecule then is called a bent molecule. That's the official name for the shape. It's bent. All right, so raise your hand if you get that. Okay. All right, how many people think that's easier than what we did last week in looking at the PowerPoint? Yeah, good, good. It would be better still if we were in the classroom and you were building this, and what I usually do is I bring the clay and sticks and I have everybody do it, and I walk around the room and I say, you've got it right, you got it right, no, you got to work on it, you got it right. So I can't do that now. I mean, I could if you guys had brought the clay. All right, then I could look at the camera and see if you got it right. I'd say I was disappointed, but I'm not. Everything is just so messed up with this virus that my expectations are not what they used to be. I'm just happy to get through the day without hurting anybody, right? Okay. All right, so let's go to this balancing act again. I forget which way is up. Is this the right way? Is that up? Or is that backwards?
Upside down.
Upside down. Okay, so how's this? Is this right side up now?
Yep.
Okay. All right, so let's look at this. We got boron trifluoride. Boron is another exception to the octet rule. It's going to be happy with 6 electrons, and it starts out with 3. It's in that right family periodic table. And this can combine with fluorines, then the fluorine here would have 7 electrons. It'd share 1. It'd keep the other 6 to itself. Then it would have 8. Same thing would happen here and here. So there you have boron trifluoride. Let's draw this over with sticks so it's a little easier to see. So you've got the boron here. Got a fluorine on top, a fluorine on the side, and a fluorine on the other side. All right. So let's go back to our clay, and remember, there's no extra electrons on the boron. That's it. All right. All right. So here we have the central boron. We'll have a fluorine over here at the end of this stick. We'll have a fluorine over here at the end of this stick. And let's put the top one in. Then we have it like this. So we've got another bond with the fluorine up here. So is this going to stay like this? Is this equidistant apart and as far apart as you can get? Take a look at it.
3 stick.
What, Donald? I couldn't hear what you said.
That was me saying stuff, Matthew, but
oh, Matthew, sorry.
On it, I'm not sure because like it'd have to be either way, and I think that's the most even. It had to be shaped like that. But,
okay, well, look at it this way. If I remove my hand here, look at this angle here. How many degrees from here to here?
180, wasn't it? Or
Yeah, 180. What's this from here to here?
That's 90.
That's 90, right? So we got two 90s and one 180. So is that equal?
No.
No. Okay. So what could I do to make three equal angles?
You'd have to like move the other one to also be in between kind of the other two, or I don't know how
Yeah.
to.
Yeah. You see why I wanted you to do it with the clay? So if because words are hard to describe, but if I just do this, there we go. Now I've got 120 here, and 120 and 120. So does that look more equal?
Yeah.
Yeah. We give this thing, and this is now trigonal planar, but this is the shape of the molecule and the shape of the electron domains both are trigonal planar because it forms a triangle here. You know, here's one side, here's another side of the triangle. There's my hand. Okay, here's the third side of the triangle over here. All right, so and look, it's all in one plane. If I tilt it this way, it's easier to see that all those they're in one plane. So that's a trigonal planar molecule. Raise your hand if you get it. Cool. I have a question for you people. Oh, where did that come from? I just did something on my blackboard I've never seen before. Okay. Nicole, why did you say dad jokes? Did I make a dad joke?
I think it was just like when you're doing, I already did the whole lesson. Do you want me to repeat it when your mic was off?
Okay, yeah, that qualifies. I didn't see that in the chat. I thought you guys didn't respond at all, so I kept going. All right, let me get back to this. Okay, so let me play the balancing act again. I take my camera. I had this worked out before, but I do have two cameras, but I can't seem to get them to work right. All right, so again, I'm going to ask that question. Are we right side up?
No, it's upside down again, I think.
Upside down again. Okay, I'll probably keep doing this because my learning curve is pretty slow. All right, so let's take this chemical here, methane, 1 carbon and 4 hydrogens. So carbons has how many electrons around it in its outer shell?
4.
4. Let's put them in. 1, 2, 3, 4. All right, so and hydrogen has how many in each hydrogen?
1.
1. Okay, so this methane molecule would look like this. One of the hydrogens will share one of its electrons. Another hydrogen will share another one of its electrons. A third hydrogen will do that. And a fourth hydrogen would do that. So let's draw this again with sticks. So you know what? I just thought of something. Oh, okay. Does that look any different to you?
It's just bigger
Yeah.
now. It's more zoomed in.
It's
Yeah,
bigger.
so
Okay, good. It's much better for me because it's bigger and I can see what I'm doing. All right. Why didn't I think of that before? Okay, all of a sudden it hit me. All right, so let's let's build this. It only took me 6-7 months to figure this out. Okay, but at least I did. All right, so let's take our 4 bonds, put them like this. All right, now careful, this is a trick question. Is this equidistant?
Yeah, I think so. Because
Yeah, at first glance you might think so, because let's measure the angles here by eye. You got 90 degrees, 90 degrees, 90 degrees. This one down here, 90 degrees. Right? All 90, right? Now, look, if I do this, then this angle from here to here is 180. Ruh-roh. That's not going to work. So what do you do with this? I really wish you were building this at home. What do you do with this? You get this right, and there's life on the planet. If you get it wrong, not so much. This is carbon, the backbone of carbon-based life forms. And if it were like this, the biochemistry we know wouldn't exist the way we know it today. Just a profound concept. The shape of one molecule determines the course of life in the universe.
would you need
What?
to like make 2 of the sticks, like have them all going like straight in one direction, like a line kind of?
Okay, tell me what to do. Tell me what to do, and I'll do it.
Like if you move 2 of the sticks are on the sides, like move them up and down, like so they're all pointing kind of in the one direction that the others are. But I don't know if that'd be right.
So
Like,
let's do. I mean, let me try this way. So you're
like kind of
suggesting
pressing
I
the
take.
sticks together, like 2 of them together and the other 2 together, so they're both like equal direction.
Okay, so you're asking me to take this and do something like this, right?
Yeah, but do it like towards the other ones, maybe, or I don't know which
All
thing.
right. Okay. Yes, Don knows the correct name for it. Can you build it? So what I did is I bent 2 of these in this direction. Now this is what I have right now. What do you want me to do next? Because we're not there yet. Take your time, think about this. Bend it towards me slightly. So which way do you want me to go? We want me to go like this? Is that it yet? Actually, we're actually pretty close. Okay, that works. You're right. Okay, so this shape is called. Don, is your mic working? Can you tell us what the shape is? I know you put it in the chat.
Yeah.
Hello, can you hear me?
It's called
Hello.
what?
It is called a tetrahedral.
Tetrahedral, right. This is tetrahedral. And all these are equidistant. I forget the numbers, 109 or 104, but they're all equal. Angles are all equal, and it spreads out the same in every direction. This is a really cool structure. And because of this, then the carbon bonds can form these long chains of carbon. All right, and that's the backbone of the carbon life form. So we have a tetrahedral. So question, what is the shape of the electron domains, and what is the shape of the molecule?
Are they the same since there's no lone pairs?
Exactly, they are the same. And that shape is, we just said it,
Tetrahedral.
tetrahedral, right? So it's tetrahedral. Okay, let's move into now I can tell it's upside down. All right. All right, so let's take a look at this. NH3. How many electrons in nitrogen?
Five.
5. 1, 2, 3. Whoop. No. You got to keep them separate, Mr. Will. Now, if you remember back when we were first introducing you to Lewis dots, I told you they had to be in the same relative positions. And that would help you out later on. And we're now at that moment. So when we put this together, if I drew this like this, that predisposes me to take a hydrogen and put it over on one side, and to put a hydrogen underneath, and put a hydrogen on the other side. So now let's draw this again with sticks, because it's a little easier to see with the sticks. What did I forget? What's over here that's not over here?
The pair at the top.
The pair at the top, the lone pair, very significant in this. All right. Okay, so that's the way you would draw the Lewis structure. Let's build the molecule now. So we'll start out with our essential nitrogen. We'll put a hydrogen in from one side, just like our drawing. We'll put a hydrogen in from the other side. And then we'll put a hydrogen in on the bottom. All right. Now, before we put the electron pair on, let's separate these equidistant in space. So 3 things in space, what would it look like?
If it was just those 3, wouldn't it be trigonal planar?
That's right. So let's make it trigonal planar like we did before. So we'll bring these up. Now we've got a nice trigonal planar. Here it is, all in one plane. All right. Now let's take our lone pair of electrons, our green balloon, and put that on top. Now what's that going to do to these 3 bonds with the hydrogens?
It should push them down, so it should make the shape tetrahedral again, right?
Ah, okay. I like that. Now, yes, it's going to make the shape of what tetrahedral? The molecule or the electron domains?
The electron domains.
That's right. Your electron domains are tetrahedral. 4 things in space, 1, 2, 3, and the balloon electrons make 4. So that's tetrahedral. Now to name the molecule, you have to remove the electrons, mentally. And what shape is this?
Trigonal pyramidal?
Yeah,
right?
it's a pyramid and a triangle. So it's trigonal pyramidal.
Trigonal.
The shape of the molecule is different than the shape of the electron domains in this particular molecule. You're going to say something? No? Okay. So there we go. Trigonal planar. Trigonal pyramidal. Sorry. Okay. So let's do another one. This is actually starting to be a little fun. It always is, but it's fun now because I'm not fighting as much with the technology. Okay, so let's build a water molecule. We've done this before for Lewis structure. So you got your oxygen. How many electrons are around the oxygen?
Sixteen.
How many?
16.
Well, outer shell is just 6.
Yeah.
Okay, so we got 1, 2, 3. Is that what you said, 6? I couldn't hear you over the connection. So there's 1, 2, 3, 4, 5, 6. Then hydrogen has how many?
1.
1. So one hydrogen can come here like this. Another hydrogen can come over here like that. And now we've got a water molecule. Let's redraw that. And let's put these lone pairs in over here. So that's our water molecule. Now let's go back and let's build it. How much smaller was the screen before I adjusted it? Just curious. Like half? Like 10%?
It's basically just the difference between either speaker view or just block view.
Okay, because I'm recording. I'm hoping this is good enough for other people to see. I don't know. Now I think it might be. I'm not so sure about the beginning. Okay, so I need another balloon. Let's try to make them the same size. Okay. Because I have 2 lone pairs of electrons this time. All right, so let's build this from scratch. We'll start with the central, take everything apart. We'll start with the central oxygen. I'll put 1 hydrogen in from one side and 1 in from the other side. And I'm sure you guys know that this isn't going to be our final molecule by now. So let's take our lone pairs, our 2 lone pairs, and we'll put them on top. Now, if I do it this way, does that look okay or too crowded?
It's okay.
What?
It's okay.
It's okay? Anyone think it's too crowded? Yeah, Nicole, what else could I do here with this? Look at how everything is. Is there any place I could spin something to get a little more room? It's all right in there.
You can move like the balloons more to the side.
Yeah, if I take these hydrogen bonds and move them like this, all right, then I've got a lot more space to deal with. All right, now they're here. We don't have the big balloons right on top of the bond. See, they're sticking out on either side. All right, it's kind of hard to see with my hand in there. All right, and how about, is there any place else I can get some more space by moving those hydrogen sticks somewhere else?
Just push them down a little.
Yeah, just push them down a little bit. All right,
Yeah.
push them down. There you go. Now we've got everything pretty much spread apart. What's the shape of these 4 things in space of the electron domains?
Tetrahedral.
Tetrahedral. That's right. They're tetrahedral. All right. So that's the name of the shape of the electron domains. How do we name the molecule again? What do I have to do?
You
What
look
do I
at it
have?
without the lone pairs.
Right. So I have to ignore the lone pairs. Now this shape here, you've seen this shape before. What's this shape called?
Bent linear.
Yeah, but just bent. All right. This is bent. Just so you know, linear would be nice and straight. This is bent. So bent's the right name. So water has a bent shape. What do you think of that? Impressed? I sure am. Okay. Okay, any questions about that so far?
No, I don't think so.
Okay. All right, so let's take a look at something else. We have, so we're on the same topic, but we're going to level it up a little bit. All right, so I've got this other handout here. Some of this is going to look familiar to you. Now, we're going to classify molecules. In this column here, I'm going to be writing the classification for a molecule, but I'm not going to tell you how this is done. I want you to be able to figure it out from the data that we give you here. So when you get it, don't call it out. I'll be asking who understands by a raise of hands. All right, so we've got our molecule we started with, the beryllium and the 2 fluorines. We know that this makes this structure here. We know we call this a linear, here it is over here, a linear shape, and it's 180 degrees. Now, the atoms that are bonded to the central atom, let's count them. This is the central atom. 1 fluorine, 2 fluorines. So 2 atoms are bonded to the central atom. Now let's look at the lone pairs of electrons on the central atom. Right? There are none. So we have 0 electrons on the central atom. The molecule type is, you ready for this? bbv2. And it's linear at 180 degrees. Raise your hand if you understand how I did that. Okay, we have one taker. All right, don't tell the rest of the class yet. 2. All right, let's go back to let's go to the next one. Tin chloride. We just made this. We have the chlorine and the central tin, and we have 2 electrons on the outer shell. We just made that, remember? It looked like this, right? Where you had the 2 bent and the electrons pair on top of it. Hope this doesn't get you too dizzy. I gotta get it. All right, so there are 2 atoms bonded to the central atom. Here they are, chlorine number 1 and chlorine number 2. And this time there is 1 lone pair of electrons. So this is called bbv2. All right, raise your hand if you think you get it now of how we get from the molecule to the type. All right, well, good. We're picking up some people. Good, very good. Okay. All right, so let's go down here. Let's look at the boron trifluoride. You've got boron in the middle. Remember, boron has an exception to the octet rule. Doesn't need 8. It's happy with 6. It'll form a bond by sharing 1 electron with this fluorine. It'll form a bond by sharing 1 electron with this fluorine, and a bond by sharing an electron with this fluorine. So let's take a quick look at that. All right, that is our trigonal planar arrangement. We've got the central boron and 1, 2, 3 fluorine atoms in a nice, trigonal planar arrangement. So that has 3 atoms bonded to the central atom, fluorine, 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 and no electrons bonded. All right. If you think you know how to name this, put it in the chat. Mm-hmm. Good, good, good. All right. All right, you guys are getting this. AB3. Okay. All right. Awesome. All right. So let's move on to the next one. We've got methane, CH4. You got 1 carbon and 4 hydrogens. All right. We built this a little while ago. It has a special name. Anybody remember what the name was? I know you know. Okay, so here we go. We've got this nice structure here. Everything should be. Let me tighten it up a little bit. You have a question, Pat?
Nope, sorry, I just left my my hand up.
Not a problem. Okay, so what's the name for this cool shape?
Tetrahedral.
That's your tetrahedral shape, right? Okay, so methane, there are 4 atoms bonded to the central atom. Here they are, hydrogen 1, hydrogen 2, hydrogen 3, hydrogen 4. And there are 0 electron pairs on the central atom. So if you think you know what this is, put it in the chat. Good, good. Anyone else? There we go, AB4. All right. Can anyone tell me what the pattern is? Like, how do we get from here to there?
A is the central atom, and then B is the bonded atoms, and then the subscript is the number of other bonded atoms.
Good. And E, like up here, E stands for what?
The lone pairs.
Right, the lone pairs. All right. So let's do another one. Let's do the ammonia. We've got NH3. You remember nitrogen had 5 electrons to start, so it's going to form 1 bond with this hydrogen, 1 bond with this hydrogen, 1 with that hydrogen, and it'll still have a lone pair up top. All right, we just built that. Let's take a look at it. So we've got our central nitrogen here, and I put a hydrogen here, and a hydrogen here, and a hydrogen here. And you might think it would be a trigonal planar, but not so much. Let's not forget about this lone pair of electrons. So you put these lone pair of electrons up here, and voila, you get this effect here. These things are going to bend out of shape. So you've got a electron domain that's tetrahedral, but hold on, I want to tighten it up a little bit. But the shape of the molecule is what? It's a pyramid, trigonal pyramidal. So let's go back to our molecule type prediction here. All right. So we've got 3 atoms bonded to the central atom, hydrogen, 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 1 lone pair of electrons. So if you think you know what this is, put it in the chat. Good. Anyone else? Good. AB3E. All right. There we go. Notice something here. Let's just backtrack a little bit. When the molecule is linear, the angle is 180 degrees. All right. When it's bent, well, we're not going to say what degrees these are because it depends on how many electron clouds we have up here. But if it's trigonal planar, the typical angle is 120 degrees. If it's tetrahedral, the angle is 109.5. All right, you do well to remember these numbers. If it's trigonal planar, then you're about 107. All right. Okay, so let's go back to our water molecule. Our water molecule had one oxygen with 6 electrons. There is, zoom in a little bit, there's 1, 2, 3, 4, then 5 and 6. It'll share 1 electron with the hydrogen, 7, and then 1 electron with this hydrogen here. So it has an octet of 8 electrons, and both hydrogens have a 1s2 configuration. All right. When we built this, hold on, I'm losing my balloons. Where'd they go? Where'd they go? You're kidding, right? Oh, there. All right. Okay. All right, so here we go. We have the water molecule, the central oxygen with bonds to 2 hydrogens here and here. And we have not one, but there it is, 2 lone pairs. This is harder than it looks. So we got 2 lone pairs like that. All right. So the shape of the electron domains is what?
Tetrahedral.
Tetrahedral. Shape of the molecule?
Bent.
Bent. Okay. All right. All right, so there we got a water molecule. It's got 2 atoms bonded to the central atom, 1, 2, and 2 lone pairs. All right, so if you think you know how to classify this molecule, put it in the chat. Good. A, B, 2, E, 2. All right, that's a 2. All right, let's level this up. Let's take a look at this one here. We've got phosphorus pentachloride. So 1, 5, and this is a hypervalent molecule. The phosphorus can have more than 8 electrons. It'll form 1 bond here, sharing with chlorine, 1 here, 1 here, 1 here, and 1 here. Let's just count the electrons for the fun of it. On the phosphorus, you got 1, 2 in this bond, 3, 4, 5, 6, 7, 8, 9, 10. So that's 2 more than an octet. That's called hypervalent. Well, we haven't built this one before, so let's do that now. So let's hold on. Cable gets in the way. All right, so we'll start with our central phosphorus, and we'll put 3 chlorines around it in a trigonal planar arrangement, just like that. There's your triangle. It's in one plane. And then we'll take 2 more chlorines. We'll put 1 from the top. And we'll put 1 in the bottom. All right, so now you have a trigonal bipyramidal. So like this forms a pyramid here. Like, look, like this. All right, you have a pyramid here. And if I put the one in the bottom, then there's another pyramid on the other side, on the bottom side. All right, so it's trigonal bipyramidal. There's just no end to this fun. Okay, so what do we have here? We have the central phosphorus and 1, 2, 3, 4, 5 atoms bonded to the central atom and no lone pairs of electrons. So put the model for this, the molecular type, in the chat. We got this. You guys are good. AB5. Awesome. Okay, we got one more. Let's take a look at sulfur hexafluoride. So we have a sulfur that will form bonds with a fluorine and another 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 fluorine. 6 fluorines. Let's just for the heck of it, let's count those electrons because it's more than an octet. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? 12. Wow. Okay, so let's take a look at what this is. So we have your clay and your sticks at home. Let's make this thing. All right. Okay, so you've got your, let's just start from scratch. It's easier. So we got our central sulfur. Let's put 4 bonds to 4 fluorines. So put one here. We'll put one on the opposite side. And we'll put one coming out of the front here like that. All right. And then we'll put one like on the other side. We'll put one coming out of the back. So there we go. There, that's the beginning of it. You've got these 4 things in space in a plane. Then we'll put another fluorine up top. And another one down the bottom like that. Right, look at that. Look at that beautiful shape. Isn't that gorgeous? Right. This has a special name. It's called an octahedral. It's an octahedral. Right. Okay, so let's go back to our worksheet here. So we've got the central sulfur with 1, 2, 3, 4, 5, 6 atoms bonded to it. There's no extra electrons on the central atom. So put the name for this in the chat, the molecular type. Here we go, AB6. All right, notice AB6, the bonds on AB6 are the bond angles are 90 degrees. The one above it, the trigonal bipyramidal, you've got 2 different angles. Some of them are 90 degrees and some are 120 degrees. All right, good. Okay. So that ends this part of the lesson for predicting bonds. Are there any questions?